Transformations. We've already looked at scaling figures, which is a dilation. So now we're going to look at 3 other transformations. We're going to look at translations, rotations, and reflections. So we've got an original figure, the Mona Lisa, right here. This is our original figure. And then we're translating this painting 2 units to the left, right? And 6 up. And I can change the number of places to the left or up, or the translation, by moving this, what's called a vector, over here. And then you can see that the way that I'm translating or sliding is shown here with these numbers. So this would mean 2 to the left and 7 up, right? So I could translate in any direction. Okay, so translations are pretty straightforward. Let's take a look at rotations. They're a little bit trickier. So I'm going to rotate this back to start. And when I rotate, normally we're going to rotate in a counterclockwise direction. So I'm going to rotate 90 degrees, and I'm going to show you what that looks like. So this is 90 degrees counterclockwise. It's pretty close, but let me get it right on 90. So let's just look and see how we can figure out what rotations are going to look like if we don't have a tool to actually do it. If you look at this bottom left point, originally, to get to it, I would go 2 to the right and 4 down. But now, and you can actually see it if you tilt your head, right? If you look at this as though this were the x-axis, this would be like 2 to the right and 4 down, right? So you keep that relationship or that distance to the origin the same when you rotate it, right? So now, instead of going 2 to the right and 4 down, now I'm going 2 up and 4 to the right, right? So they're gonna, and if you look at the coordinates at the points, now they've switched places, and the y value, what was originally the y value, has changed its sign, right? And now it's the x value, and it's become positive. Let me go another 90 degrees. So now I'm going to keep going. Let's go to 180. And I can't get it right on 180, so let me just type it in. Okay, so now here's 180 degrees. And if you notice, the relationship to that origin is still the same, right? So if you look at the top of the painting goes above the x-axis, right? Just a little bit. And here, the top of the painting dips below the x-axis, just a little bit, by the same amount, right? Another thing that's important with rotations is to note that this point that we're tracing, we could trace any of the points, but we're just opting to trace this one point. This one point will have the same distance to the center of that circle at any point in the rotation, right? Because it's the radius of the circle. When you find the distance from any point on the circle to the center, that's the radius. So that distance is going to stay the same whether it's here or here or here or here or here. If I were to draw a line from that point to the center, in any of those places, it would be the same distance from this point to the center, right? Another thing to keep in mind with rotations is that the figure doesn't change its shape or its size. These are congruent figures, right? They have the same length, the same width, the same area, the same angle measures. All of that is preserved. So when we rotate, the angles are all still the same. The shape is still the same. The size is still the same. The only thing that's changing is the placement, where it is on the coordinate grid. Another thing to notice about 180-degree rotation is that the figure's now upside down. But not only is it upside down, but it's not like right on top of itself. So it's not like we took it and like flipped it up. It's upside down and it's kind of like moved over, right? So we could also get that same transformation by, flipping it and then shifting it. But this is how we can get it in just one move, right? We can get to that new position by just rotating 180 degrees about 0, 0. All right, and then the last transformation I want to look at here is reflecting. So reflections are also referred to as mirror images, right? So we are flipping over the line. So let's look, this one's a little bit more complicated. I would like to look at just flipping over the y-axis first. So with reflections, it's important to note that this point has a distance to the line of reflection, and it's going to be equal to this point's distance to the line of reflection, right? This point is 2 units away from the yellow line of reflection. This point is 2 units away. Our original point here is 5 units from the line of reflection, so its reflected image is 5 units from the line of reflection. So those corresponding points are going to be the same distance from the line of reflection on both sides. So if you need to reflect something, a really easy way to reflect something would be to count how many points it is from the line and then go that many spaces in the opposite direction away from the line. And bam, you've got a reflection. Let's see what this would look like if we reflected over the x-axis. Now to do that, I'm going to move my original drawing down just a bit. Let's put it right there, right? So I'm going to reflect over the x-axis now. There it is. So now my figure, where before when I reflected over the y-axis, it looked backwards. Now, since I reflect over the x-axis, my figure looks flipped upside down, right? It's kind of flipped on its head. So, but again, the same thing happens, that this corner is the same distance from the yellow line as this corner. And this point is the same distance from the yellow line as this point, right? Those corresponding points still have the same distances, congruent distances to the line of reflection. These 3 transformations that we looked at, translations, rotations, and reflections, all preserve size and shape, which means we're using congruent figures here. When we rotate, when we translate, when we reflect, we're getting a congruent figure. It's just in a different location. When a transformation preserves size and shape, it's called a rigid transformation. Okay, notice that I'm not including dilations in this discussion because dilations change the size, right? But translations, rotations, and reflections are all called rigid transformations. They keep the same size and shape of the original figure. So the pre-image is what we start with. The image is what we get after the transformation. And with a rigid transformation, the pre-image and the image are congruent. Okay, and that's rotations, translations, and reflections, those 3. All right, so we have an original polygon that we're given, and we have to choose which picture, which image shows a translation, a rotation, or a reflection. So let's start with translation. A translation is just a slide, right? So it preserves not only the size and shape, which they all do, but it also preserves the orientation. What that means is, if I've got this angle here, oh, sorry about that. If I've got this angle here that looks like a squished L, then, and it's on the left side of the figure, it's going to stay on the left side of the figure. If I've got these two angles here that are right angles that are on the right side of the figure, then they're going to stay on the right side of the figure. So when I translate, I preserve the orientation, which means I'm not turning it or I'm not flipping it, right? So the only one that looks identical to my starting figure is this one. So this one is a translation. I'll just put TR for now. Now when I'm looking for a rotation, I mean, it's kind of helpful that I can actually rotate this figure. So I could take this figure since I'm in PowerPoint and I could rotate it, right? So that would be 90 degrees. And then here we would have 180 degrees. And then this would be 270. And then 360 brings us back to start. So now, did any of those look like one of the figures that we see below? Well, I'm going to do it again. I can rotate 90 degrees counterclockwise, and I see that, yeah, this looks like the one right underneath it, right? So that means that answer choice A is a rotation. And so I'm just going to write ROT for this one. All right, and then that just leaves C. So C must be a reflection. But let me put my figure back to where it was originally. So originally it was like this, right? That's my original polygon. So where can we see a reflection? Well, it looks like the image that's in C is upside down, right? So it looks like maybe we flipped right around this line. If this is our line of reflection, then that means that this point and this point are right on the line of reflection, right? So they don't have anywhere to go. This point is 3 away, it's 3 below, so when I reflect it, it's now going to be 3 above. This one is 3 below, so it's also going to be 3 above. And then if I draw a figure in there, if I connect my dots, then that's exactly what we've got over here. So this one, let me just undo that. So this one is definitely the reflection. Which pair of triangles shows a reflection? So remember that the property of a reflection is that the points that are corresponding are going to be the same distance on both sides from that line of reflection. We're looking for the object either to be flipped this way, right? So it might appear backwards, or this way, so it might appear upside down. In this figure on the left, we've got A, B, C, and notice that it's hard to see, but these letters have a little apostrophe behind them. A prime, B prime, C prime. That means that this is the original figure, this is the pre-image, and this is the image. This looks like it was just slid. So this one to me looks like a translation. This one over here on the right, here's my right angle. Actually, this is my original figure, right? ABC. And my right angle has been turned up here, right? So this looks like a rotation to me. So actually, let me see if I can rotate that and see. So if I were to rotate this, yeah, that's how that figure is, right? It's got the orientation where the right angle is up in the upper right, where the right angle initially started in the upper left, but after a 90-degree clockwise rotation, now it's in the upper right. So this is definitely a rotation, and we could either go 90 degrees clockwise, or I could go 1, 2, 3, which is 270 degrees counterclockwise. All right, let's put that one back. So this is a rotation. That means that this one must be the reflection, but let's take a little bit closer look to see why it's a reflection. So this point C, which is my original point, is 2 units from the y-axis. The image point, C prime, is also 2 units from the y-axis. And those distances, when you're finding distance to the y-axis, they're always perpendicular, by the way. So we could do the same thing. A is 1, 2, 3, 4, 5, 6 units. So A prime must be 1, 2, 3, 4, 5, 6 units in the opposite direction. B is 3 units away, so B prime is 3 units away in the opposite direction. And these are all perpendicular lines, right? These all form right angles. So this one is definitely the one that shows a reflection. The smallest angle in triangle A is 20 degrees. So that would be this angle right here, because the smallest angle is always across from the smallest side. Triangle A was rotated to form triangle B. What is the measure of the smallest angle in triangle B? So remember, we talked about when we do rotations, the angle measures don't change, right? The size and shape, neither of those things change. So if it's 20 degrees here, then when I rotate it down to form triangle B, it's still going to be 20 degrees down here. So that's the answer to the first part. The measure of the smallest angle is still 20 degrees. So what would the angle of rotation be? Well, the angle of rotation would be, let's take a look at it. So we've got this, it looks like our longest side is the top here, and the longest side is the bottom here. So if I rotate this until that longest side is the bottom, this would be 90, and this would be 180. So it was a 180-degree rotation that would take that longest side from being on the top to now being on the bottom. What set of transformations is performed on triangle ABC to form triangle 3? So here's triangle ABC down here, and we're trying to get to triangle 3. So I could, now just disregard triangles 1 and 2. We don't need those right now. They're just extra information. So it looks like something that I just looked at. It looks like a 180-degree rotation, right? So let's check that out. Keep your eye on this triangle, and we want it to look like this one, right? So if I rotate this 180 degrees, that would be 90 and then 180. Yep, that looks like it's right. But it's a little off, right? Because when I rotate it, I notice that my original point A is not on the axis, and my new image point is, right? So this point A is 1 away. This one is right on the axis. So it looks like I would need to translate my triangle 1 unit to the right, right? So that would be my new triangle. And then rotate it. So now let's see if it looks like this one. So now I'm going to rotate it 180 degrees again. Oh, it didn't stay with my drawing. All right, I'll rotate it and then I'll draw it again. And my triangle that was originally down here, but now I rotated it. So now it would be right here. And that looks like the other triangle before I did the rotation, right? So that would be the key. So for this one, let me get rid of that and let me rotate it back again. we would have to translate, hold on, we would have to translate 1 unit to the right and then rotate. Or, as you saw, we could rotate and then translate, right? But if we rotate first, if I rotate this first, I would now have to translate to the left to get this point A on the axis. Okay? So it would be a rotation and a translation that we would need to do here.